Today we'll look at the second law of thermodynamics and recall that energy transfer really depends on the interaction between molecules. So basically it occurs at a molecular level. So if we look at a system that's isolated, so for example an ideal gas, then the particles with the higher momentum are involved in more collisions, and therefore energy is most likely transferred from these molecules with a higher kinetic energy than those with a lower kinetic energy. So we can say that energy transfer is probabilistic. Now if we look at the interaction between two objects, then a transfer of thermal energy, namely heat, is going to occur from the object with a higher average kinetic energy compared to the object with a lower average kinetic energy. So given that the energy transfer is probabilistic, we say that both objects are most likely to have the same temperature after many collisions between their molecules occur. And this leads us to the second law of thermodynamics, or at least one interpretation of it, and that is that heat transfer from a cold body to a body with a higher temperature is impossible. And this is the postulate of Clausius. So effectively heat's going to be transferred from the hotter object to the colder object. And this leads us to entropy, which is another state variable represented by the letter S and is defined as the ratio of the heat to the temperature of a system. Then if you go through a cyclic process, then a change in entropy is going to be 0. So this tells us that entropy as a state variable is also path independent. Now we can interpret entropy as a measure of disorder in a system. And looking at an example, so if we have two containers of gas and then we remove the boundary between them, so we end up with something like this, well, the entropy or disorder is going to increase in this system. So in other words, the boxes here with a high degree of order become disordered. So you can imagine that these gas molecules are going to be flying around at different speeds, and the top configuration over here is more likely than the bottom one, because the bottom one is more structured, as we can see. So consequently entropy can be viewed as certain parts of the system are not available to do work. And this leads us to Kelvin's postulate on the second law of thermodynamics. So Kelvin stated that the transfer of heat completely into work is impossible. So this here is Kelvin's postulate. And a typical example is if you look at a piston in a car and you have the combustion of a fuel-air mixture. So if you have a fuel mixed with air and that gets ignited by a spark due to a spark plug, so what happens is that part of this mixture is going to combust. So you're going to get an explosion that pushes this piston down, that's connected to a mechanism that rotates the tires of the car. And the unburned gas is going to result in exhaust fumes. Okay, so this goes out of the exhaust pipe. And this is a consequence of the entropy of a gas. So it's not going to be arranged in such a way where all of these molecules are going to combust. There's going to be waste occurring. Okay, so some of this explosion is going to be transferred into work and some into exhaust fumes. So another way that the second law of thermodynamics can be stated is the total entropy of a system plus its surroundings will never decrease. So for example, if you can imagine that a liquid with these water molecules turns to ice, okay, so this is H2O liquid to a solid. Well, the system here of water that turned to ice loses entropy, so it becomes more ordered. but consequently, it releases heat into the environment, and therefore the environment gains entropy or becomes more disordered. And another example is if you have a ball landing on a surface, well, you may see nothing at the macroscopic level, but at the microscopic level, the surface is going to have some roughness, and the molecules are going to be arranged in a certain way. So when this ball collides with the surface at the molecular level, you're going to get some disorder that you're not going to see in the real world. So entropy is going to always increase. So consequently, the entropy of the universe, so that's the entire universe, is always increasing. And we'll use these interpretations in subsequent videos involving the second law of thermodynamics.